A new paper came out this week on mastication. Let's have a look. Here is that paper on mastication or chewing. The focus of the paper is on the energetics of mastication. That is, how much energy does it require to chew your food versus how much energy do you get out of the food. It's an interesting engineering problem, but the entire paper, the entire study is cast into an evolutionary framework. Let's look at the introduction here. Our ancestors' ability to effectively acquire, process, and consume food underpinned their survival, and changes in their masticatory system played a key role in the evolution of our own species. Skipping down, the need to optimize feeding so as to extract maximal energy from food sources without wasting it on processing costs is one of the main driving forces behind the evolution of mammalian mastication. Now, how do they know these things? How do they know that evolution was going on here, and that the masticatory system played a key role in the evolution of our own species, and that this optimizing feeding was a main driving force behind the evolution of mammalian mastication? How do they know these things? Well, they do have two citations here. Okay, let's have a look here at our citations. One is from 1977. A dentist wrote that. The other is 1997. Let's have a look at that 1997 paper, an optimization model for mastication and swallowing in mammals. Okay, that sounds interesting. They are going to argue that there's an optimization problem. And here's the summary. Our model suggests that there is an optimum moment for a mammal to swallow, and they're going to explain that. So there's an optimization problem. That's interesting. Sounds complicated. The first paragraph of the introduction lays out a challenge, the challenge for mammalian mastication and digestion. The problem is that mammals need more energy than reptiles, so how are they going to get that out of the food? They are going, the obvious solution, or an apparent solution there, is to crush the food into smaller particles. And so that's the solution. However, it is a complex problem to solve, and it is a challenge for evolution. Therefore, it's not an easy thing to do, this chewing of food. And that's what they say here in the next paragraph. This involved a large anatomical and physiological changes. Okay, so a challenge. Now, crushing the food into smaller particles is only part of it. You also need lubrication. This lubrication is going to form a ball, or what they call the bolus, and that will help it go down to the stomach. So you need these two things, crushing of the food and the lubrication. And so they talk about these two thresholds. There's two thresholds that must be satisfied before swallowing can be initiated: a food particle size threshold and a lubrication threshold. Okay, interesting. So you get more challenges for evolution. Evolution is going to have to design this system, create this system that solves two different problems simultaneously. But actually there's another function, another requirement here that they talk about, and that is this problem of the food goes down a pathway that intersects with the airway. And it's very important. This can be fatal if that food or part of that bolus gets into the airway, goes down into our lungs. We all know what that's like, a very uncomfortable feeling of it going down the wrong pipe. So it's very important that this criteria be met as well. The lubrication will help on this, the food particle size will help on this, but it's got to not be food particles must not splinter off from the bolus. So there are a lot of challenges for evolution. As we saw, you need these large anatomical and physiological changes just to get the chewing system in place. You need to have simultaneous lubrication, and you need to have these particles stick together as they pass through the airway so you don't get these things into your lungs. You need food going into your lungs. So what are they going to say about this? Skipping down, the problem is solved to some extent by a very rapid swallowing action, but by forming an adherent food mass, the risk of inhaling food must be greatly reduced. We suggest here that the endpoint of mastication is marked by a peak in the cohesive force that binds food particles together. So that's kind of their basic thesis here, is that's driving the problem, this this need for a cohesive bolus. And so here's how I've drawn it notionally. On the x-axis, you have time there. That's your chewing. And as you chew, particle sizes are getting smaller and the lubrication is increasing, and that's building up this cohesive force in the bolus. But over time, you hit a maximum, and at some point you over-lubricate, and you can start to break down this bolus, and so it gets to be not so good. So there's this peak cohesive force point, and that's when you need to swallow. We suggest that the peak cohesive force between food particles is the optimum time to swallow. And the turning point in the cohesive force, the moment when cohesive starts to reduce, may be what is actually sensed. Okay, so you need a sensing system too. Okay, more challenges for evolution. Early mammals developed post-canine teeth capable of reducing food particle sizes. In order to control particles, they also developed increased mobility of the tongue and developed muscular cheeks. Okay, a lot more things that evolution has to do, and has to do fast and simultaneously to get this system up and running. Skipping down, small particles are much more likely to get misdirected. Early mammals evolving a masticatory apparatus must, therefore, also have been under strong selective pressure to evolve a safe anatomical pathway for foods that was separate from the airway. Okay, more complications. Skipping down, thus, early during mammalian evolution, a palate developed to seal off the upper respiratory tract, and in the pharyngeal region, a whole set of constrictor muscles were developed, which have no homologs in reptiles. The requirements for evolution are just getting bigger and bigger as we dive into this. There was and is therefore an active need to detect the state of these particles in the mouth in order to safely swallow. Thus, even though swallowing is known to be controlled by brainstem circuitry producing stereotyped motor behavior, peripheral feedback must be extremely important. Okay, so you need the whole sensing system in place. So we can add yet more challenges to the three that we had earlier: optimizing the swallow time, increased tongue mobility, stronger cheeks, safe pathway separate from the airway, a set of constrictor muscles, peripheral feedback nerves to monitor the chewing. A lot of things have to happen, and they have to happen simultaneously or very quickly for this to work. This is very difficult for blind mutations to pull this off. It's a tall order. It's not likely. The science is contradicting this, not confirming this. And the paper which is cited does nothing to reckon with these challenges. It does not demonstrate, it does not show, it does not even suggest feasible ways that evolution could do this. So back to today's paper that we were looking at, this cost of chewing paper, and these, again, the paper starts right off here. Our ancestors' ability to effectively acquire, process, and consume food underpin their survival, and changes in their masticatory system played a key role in what? The evolution of our own species. How do they know that? The need to optimize feeding so as to extract maximal energy from food sources without wasting it on processing costs is one of the main driving forces behind what? The evolution of mammalian mastication. Was that one of the main driving forces behind mammalian evolution? The evolution of mammalian mastication? Citations 1 and 2 do nothing to support these claims. These are unfounded claims. This is not atypical. This is typical. This is what you find in the evolution literature. I'm just looking at a paper that came out last week. I didn't pick this out for any particular reason. This is typical in the evolution literature. It is a vast literature of papers falsely citing other papers as having demonstrated evolution, thus justifying the new work. But the cited papers do nothing of the sort. Now let's look at some more passages from this week's paper here. This has led to substantial morphological innovations in mammalian teeth, jaws, pharynges, and masticatory muscles. Okay, more challenges for the evolutionary process. Substantial morphological innovations that those blind mutations had to come up with somehow, by some unexplained manner. Mastication is a kinematically complex process involving both vertical and lateral movements of the mandible in a cyclical manner with repetitive closure of jaws. That's a very complicated process. Skipping down, chewing evolved some 260 million years ago and is associated with a range of vertebrate taxa. The precise occlusion and lateral movements that distinguish mammalian mastication, however, is a remarkable evolutionary novelty. So, more of a tall order for those blind mutations, a remarkable novelty. So, that's a look at a typical evolutionary paper talking about how X evolved, but really not explaining how X evolved at all, but rather presupposing that it evolved. Now, as I went through these passages, I hope you also saw the teleological language which is pervasive and ubiquitous in the literature. And I'll go back, let's look at those examples. The need to optimize feeding. They talked about optimizing. Evolution is optimizing a problem here. In order to achieve rapid particle size reduction rates, there were large anatomical and physiological changes that evolved. The infinitive form is, as usual, the giveaway there, to achieve, in order to achieve rapid particle size reduction. So that's the goal. There's the teleology. Evolution was achieving a goal, this rapid particle size reduction rate. Aha. The problem is solved to some extent by a very rapid swallowing action. Okay, evolution is solving a problem. It's got a problem in mind. Natural selection has energetically optimized the human chewing apparatus. Natural selection is like this engineer tinkering away, working away, solving problems. This is teleological. In order to control particles, they being early mammals, in order to control particles, early mammals also developed increased mobility of the tongue and the muscle cheeks. So in order to control, the infinitive form, evolution had a problem to solve and it solved it. Those early mammals were also under strong selective pressure to evolve a safe anatomical pathway. Aha! So selection had this goal in mind, this pressure to evolve. Come on, you mutations, you've got to come up, you blind mutations. You need to come up with a safe anatomical pathway. There's pressure here. Do this now. Very teleological. And so, what? A palate developed to what? To seal, the infinitive form. A palate developed to seal off the upper respiratory tract. That infinitive form tells you the goal. That's the teleology. A palate evolved to seal off the upper respiratory tract. This is phony science. Religion drives science, and it matters.